everyone, thank you so much for clicking onto the video. And we're going to look at some harder questions for electrochemical cells. So it says to use the table below to answer the questions. For A, select the species which is the most powerful reducing agent. So the meaning of reducing agent is something that loses electrons. So it's an electron donor, because the thing that's being reduced gains electrons, and so reducing agent is an electron donor. And first of all, what we think is a half cell that has a more negative standard electrode potential have a better reducing agent than the more positive standard electrode potential, or is it the other way around? And well, when we connect up two half cells, the half cell with the most negative standard electrode potential, electrons will come from there to the more positive one. And so there's our answer. So that means that we're looking at this zinc half cell at the top because it's the most negative. So that means it gives its electrons more easily. And so there's a better reducing agent in that half cell. And now we have to choose between Zn2 plus or the zinc. And now we think which one is actually losing the electrons and which one is gaining the electrons. And so zinc has to gain electrons to form Zn, like this equation here. But however, zinc has to lose electrons to form Zn2 plus, and that means that the reducing agent in this half cell is the zinc, because we have the half equation zinc goes to form Zn2 plus 2 electrons. So these 2 electrons here are getting donated to the thing that it's reducing, so the other half cell. And so our most powerful reducing agent is zinc. And then for B, select a species which an acidic solution will reduce VO2 plus to VO2 plus, but will not reduce VO2 plus to V3 plus. First of all, the in acidic solution bit just means that there are H plus ions. And so if we want something that will reduce VO2 plus to VO2 plus, we need a half cell with a more negative standard electrode potential. And if we want something that doesn't reduce VO2 plus to V3 plus, then we need a half cell with a standard electrode potential which is more positive than this half cell. And so if we find these two equations, so we've got this equation here and this equation. So this is the equation they number first. So I'm going to call that number 1. So that's going to be number 1. And then this is going to be equation 2, just as they've listed it. And so we need a half cell which is more negative than equation 1, but less negative than equation 2. So that means that the species is in this Fe3 plus Fe2 plus half cell, because it can reduce equation 1 but not equation 2, because it's in the middle. The standard electrode potential is in the middle. And so now we pick one of the equations. So I'm going to look at the first equation. So the standard electrode potential, which is underneath the Fe3 plus Fe2 plus. Now that one is being reduced. So that means that the VO2 plus ion is gaining the electrons, like how they've written it in this equation. So that's what's happening. So we must have this equation but reversed, because electrons need to be given to the VO2 plus half cell from the Fe2 plus Fe3 plus. So that means that Fe2 plus is going to be forming Fe3 plus and the electrons. And so the answer of the species that will reduce the VO2 plus to VO2 plus, but will not reduce VO2 plus to V3 plus, is Fe2 plus. We can always check this with the other equation as well. So with the other equation, what's happening is that it's being oxidized because it's not being reduced. So the reverse of equation 2 is happening because it's giving away its electrons. And so that means that the Fe3 plus is accepting the electrons. So the species that will not reduce the V2 plus to V3 plus is still the Fe2 plus. So that is our answer. For C, select a species which in acidic solution will oxidize VO2 plus to VO2 plus. So to oxidize something, we need that half cell to have a more positive standard electrode potential. And so the more positive one is in here. So now we know that it's in this chlorine chloride half cell. So now we need to work out between chlorine and chloride which one is the oxidizing agent. And so the oxidizing agent is the electron acceptor. And so from this equation, we can see that chlorine is the electron acceptor because we're adding on 2 electrons to form chloride ions. And so our answer is chlorine. So before I move on to question 2, feel free to pause the video and try it for yourself first. Use the standard electric potential data given in the table below to answer the questions which follow. For A, an excess of potassium manganate was added to a solution containing V2 plus ions. Determine the vanadium species present in the solution at the end of this reaction, and state the oxidation state of vanadium in this species and write a half equation for its formation from V2 plus. Okay, so if we add more potassium manganates, that means we're adding more MnO4 minus ions. And so we can see in this equation here that we would have more of these MnO4 minus ions. And so if we have this connected up to this V2 plus here, if we have these 2 half cells connected up, because the V2 plus V3 plus half cell has a more negative standard electrode potential, this minus 0.26 compared to this 1.52, that means that the V2 plus V3 plus half cell would reduce the MnO4 minus Mn2 plus half cell. And so what happens is that because the V2 plus V3 plus half cell reduces, that means that it gives out the electrons. And so the equation that's happening is that V2 plus is being turned into V3 plus the electrons. So these electrons are now transferred to this to the MnO4 minus to produce this Mn2 plus. And so if we have an excess of potassium manganate, first of all, the V2 plus will turn into V3 plus. And then if we look further at the equations, we have a V3 plus here. And if we add this with water, then we form VO2 plus. And because this manganate produces water in this reaction, this water then reacts with the V3 plus that we formed here. And so what happens is that the V3 plus then turns into VO2 plus ions. And then again, this VO2 plus added with water, it then forms as VO2 plus. So if we've got the excess of potassium manganate, more and more water is formed. And so this VO2 plus will then turn into VO2 plus. And of course, this is also because all of these equations with the vanadium, they all have a more negative standard electrode potential, so that they always act as the reducing agent. And so that's why eventually the V2 plus will turn into this VO2 plus. So for A, determine the vanadium species present at the end, that would be the VO2 plus. And now we need to state the oxidation state of it. So if you don't remember how to find the oxidation state, then quickly go back to the redox videos and then come back. So we have the VO2 plus and oxygen is nearly always -2, as we've learned as one of the rules. So we have -2, and then we have 2 of the oxygens, so we have another -2. And then we have x -2 equals +1, because +1 is the overall charge. And so x is equal to +3. So the oxidation state of vanadium must be +3. And now write a half equation for its formation from V2+. So again, if you can't remember how to write half equations, quickly go back to the redox videos and then come back. So we have V2+, and that's going to form VO2+. And so I'm just going to do this quickly. So we'll balance the vanadiums, that's already done, then balance the oxygens. So we've got 2 waters, and then we have 4 H pluses, and then this charge is +5, and this charge is +2. So that means we need 3 electrons on this side. And now it should be balanced. And then for B, the cell represented below was set up under standard conditions. Calculate the EMF of this cell and state with an explanation how this EMF will change if the concentration of Fe3+ ions is increased. So here we have the H2SO3 cell, so this one, and then the Fe3+ Fe2+. So again, because the H2SO3 half cell has a more negative standard electric potential, that's the one which will be reducing the Fe3+ Fe2+. So that means that to find out the EMF, what we do is that we do the standard electric potential of the right minus the standard electric potential of the left. And this comes out to be 0.77 minus 0.17, and that equals plus 0.60 volts. And then we're asked how this EMF will change if the concentration of Fe3+ ions is increased. And so what happens is that when, so firstly, the H2SO3 and SO42- half cell is reducing the Fe3+ Fe2+. So it's reducing the Fe3+ ion by giving it an electron to form the Fe2+ ion. And so if we increase the concentration of Fe3+, that means there are more of them to accept electrons. And so they accept more and more electrons, and that makes its standard electric potential even more positive. And so what that does is that if we look at this equation here, so we have EMF is the standard electric potential of the right minus the standard electric potential of the left. If this is now bigger and this has remained the same, then that means that the overall EMF of the cell will increase, because there are more of the Fe3+ ions to accept loads and loads of electrons, so its standard electric potential is bigger.